my report is about adhesion. It's the mostly experimental work, but we also tried to make some very simple mathematical model to describe all effects. Not all, but some effects which was experimented, was observed experimented. Here are some several examples of adhesion. Adhesion is very important in some biological systems. For example, this view, this house is some plants can grow up to 30 meters with using of special roots with very good connection between the root and the wall, but it's actually it's adhesive but glued contact. You can detach it after attachment and solidification, and if you attach you can't if you detach you can't attach these things. Some bacteria use to connect between bacteria and organs. Our organs consist of a lot of cells which use adhesion to make these organs, and it's also useful for many technological processes as soldering, for example, painting, and some animals can use the adhesion as gecko, you can see here, to move along the walls at different angles, and at the tails it can be also. They can do it also, but they need to have one mechanism how they can clean this adhesive fits, and they have this. For example, here you can see several examples of different animals, and this picture is very interesting. If we tell about contacts, it's very important the properties of two bodies in the contact, and you can see here the contact between wood and foot. It's has different properties, but this contact between frog and foot, it's maybe we can use here this elastic similarity properties to describe independently normal and tangential contact, because it's approximately the same objects. So if I use some photos from internet, for example, it was here, and this left foot is a normal contact, but I don't know how it was done, these photos. Maybe it was done in such a position, and it's then tangential contact. But actually we know that animals can move at different angles, and there are a lot of works and classical theories as Jakov, DMT for normal contact. For tangential contact, there are a lot of models. There are also some models and experiments for motion under the angle, but it's not a lot of works investigate this contact. We developed an experimental device which can perform the normal indentation with this linear motor 1, tangential indentation with linear motor 2. We observe through transparent rubber what happens in the contact. And actually it's very easy. It's contact between steel indenter and rubber. And we have here also rotation stage 8. Due to using of this rotation stage, we have quasi 3 coordinates. You can see here a small example of working of our device. With our device, we can make experiments with different loading scenarios. Because we have all 3 coordinates. It's actually rotation tribometer, linear tribometer, and just normal indentation can be performed also. So here we save with this program coordinates of these letters in the usual Cartesian coordinates. Because of we use this rotation stage, we need this in polar coordinates, radius, vector, and angle. And we can, in principle, use our device as a usual plotter, usual simple plotter, due to this rotation. But it's just demonstration, of course. Here we use motion in tangential direction, in normal direction, just to bring pen in the contact and detach from the paper. And rotation, due to rotation, we have this third coordinate. We need this to write. Okay, that's next. Is a schema of our experiment. We investigated 2 situations. It's indentation of indenter in rubber layer, scenario A, at motion in this direction in indentation, and we have investigated also situation with detachment with the same velocity, but indenter was moved with different normal and tangential velocities. This linear velocity was 1 micrometer per second to have the quasi-static contact. But if we have different angle of alpha, we have different normal and tangential components of velocity, and so we have motion of indenter at angle. Here you can see a video, or you can see video. Maybe I need to start here. And just video of indentation in normal direction. Here's the dependencies of normal force and contact area. Because we saved our pictures with contact area, we can calculate the contact area. If we have contact area, we can calculate the dependencies of tangential force if we have tangential contact, and average pressure. It's also very important, and it was interesting to look what happens in the contact. Here we can see that we have the secondary adhesive hysteresis. This red line is indentation. Adhesion is very weak at indentation, and at detachment adhesion is very significant. Because of this, we have negative values of normal force is also well-known effect. And here is dependencies, experimental dependencies for normal force, contact area, and we have not a very perfectly circle contact because it's real experiment. Because of this, we also calculated this diameters of the contact in this direction and in this direction. For normal contact, it's not important how we in which directions we calculate this sizes of the contact, but during tangential motion, we move indenter in this direction, so L horizontal is coincide with the direction of tangential moment. Here you can see the video for tangential. It's just indentation to fixed indentation depth, and then motion with very small velocity in one direction. And you can see that normal force is approximately constant because of indentation depth is constant also. We have approximately constant shear force in principle, and jump-like changes of the contact area. And we can see here that we have completely different behavior at the rear front of the contact, this side, jump-like indentation of rubber, and this back contact, we have just smooth detachment of the rubber. Okay, here there are experimental dependencies, and we also made a lot of different experiments. And for this system, independently on indentation depths, we have constant tangential stresses. For example, here, so friction force depends on the contact area. It's also well-known regime. Okay, and next, it's already experiments results for motion and the angle, it's indentation. For example, for normal force, we have increasing of normal force to approximately the same value, but the velocity of increasing of normal force is different. For example, alpha, it's 10 grad. 10 grad, it's near the tangential motion. And indenter need more time to reach the maximal indentation depth. Indentation depth for all these experiments was 0.3 millimeter. So if we make normal indentation, we need shortest time, but for this 10 grad, we need more time to reach this value of indentation depth. And it's also interesting here. In principle, we have observed at investigation of tangential contact that we have sliding regime if this tangential stresses exceeds critical value. And here we have sliding regime only for, this tangential stresses, only for value alpha 10 grad, its critical value about 45 kilopascal, and for all another angles, this tau reach not critical value. For example, this point, this point, this point. It's a point at which we indented the indenter to the maximum indentation depth, and after this we moved it up in normal direction. Also, it's motion at the angle experiment scenario B. In this scenario B, scenario A it was indentation. Scenario B, it is detachment under the angle. We performed indentation to this maximal indentation depth 0.3 millimeter, and we detach indenter from the rubber also at different angles. So for this case, for 90 degrees, we have the same situation as before, but for another values of alpha, we have different behavior in comparison with previous case, because in this case we performed indentation in normal direction to the maximum indentation depth, and after beginning of the motion at the angle, we have only detachment of the rubber from indenter. The rubber don't attach during this motion, so we have smooth decreasing of contact area. In all cases, during this normal indentation depth, we have increasing of contact area to 45 millimeters square, and then smooth decreasing. In the previous case, it was not smooth decreasing. For 10 grad, for example, you can see here jump-like attachment of the new fresh rubber surfaces to the indenter. We constructed some simple model based on method of dimensionality reduction. Professor Popov had today the presentation about the dimensionality reduction, and he has shown that we can obtain with this method a perfect solution for JKR theories, for JKR results for this adhesive contact. From experiment, we know that we have more or less constant tangential stresses. This is procedure, how we can calculate tangential contact stresses in our model, how we can apply this. This tangential stresses is ratio between the friction force, this tangential force and area of contact. And this friction, tangential force is sum from forces from all elongated springs. So we have some criterion if the elongation of some springs more than P r tau 0 divided by 2G, we have sliding. Those springs must slide. It's a function of radius of the contact R. Because of this, we will have different behavior at different loading scenarios. And with using of those formulas, we have constructed in principle this no sliding diagram. And for this scenario R, we can see that we have sliding only if this alpha, this angle is lower than approximately 20 grad. And we have observed the sliding regime in our experiments at 10 grad. At 20 grad, we have not observed this sliding, this global sliding, I mean. And this for scenario B, this indentation to 0.3 millimeter, we have here more areas. This sliding in, no sliding in. If we perform further indentation at the motion in the rubber, we have not done this experiments. And here, this no sliding out if we realize detachment, as in our experiment. So you can see here comparison between theory and experiments for scenario of loading R. I have shown here the dependencies for this tangential force, for contact area, and for this tau tangential stresses. You can see that there are a lot of, they have in principle the same form. Of course, it's a very easy model. In MDR, for example, this contact area is circle. In experiments, it is not circle. And because of this, we have some differences between those results. But in principle, if we have no sliding, for these big angles near the normal indentation, here, here, and here, we have the same form. Because we have problem when we have sliding. There are a lot of dynamic complex effects as elastic waves propagation, for example, and changing of the area of the contact. We can't describe this in MDR. And here the comparison between theory and experiment for indentation experiments. In principle, we have here, for example, for the small angles, different shapes of curves, but for big indentation angels near the normal contact, we have good comparison. And also we have here different values on this axis. I did not show this normal force, for tangential force and for normal force also, because we have constructed our model for half space and we have done experiments for layer. We had a rubber layer with thickness of 5 millimeters. So our rubber layer had bigger stiffness than half space. Because of this, we got in model lower values of forces because of lower stiffness. But for example, here also in simulation and experiment, we have sliding mode with constant tangential stresses approximately for all angles. And with indentation, we have the sliding mode only for angles very near the tangential motion. In principle, the last slide with video, it's a real video from experiment. You can see what happens in the contact for different angles. It's real pictures from experiment. Normal force, shear tangential force, contact area. It was calculated with special computer program. And just ratio, it's average contact ratio. It's ratio between normal force and contact area. And this tangential stresses, it's also ratio between tangential force and contact area. And here this alpha 60 grad. Next it will be alpha 50 grad. And we have, in principle, approximately the same behavior for all different angles, but if alpha is very small, 10 grad, it will be last video. In this last value, you will see that we have jump-like propagation of the contact here on the rear edge of the contact and on the back side. For input tangential contact, we have observed jump-like propagation only on the front, on the rear front of the contact. But here we perform not only tangential motion, also indentation depths, also indentation normal direction. So contact area should be bigger and bigger at this side, and this side also. And it's also interesting after now it's 20 grad, it's 10 grad the last. For 10 grad, we have observed really jump-like propagation of the contact, but we did not observe jump-like change for friction force. If fresh area of the rubber go to the contact, it's also in normal direction, it's jump-like, and these new areas of the rubber have no tangential loading. They become tangential loading due to further motion in this tangential direction. Because of this, we have here jump-like changes of averaged values of tangential stresses, but it's not physical effect because we just divide friction force divided by contact area, but contact area propagates jump-like. And we have here non-homogeneous distribution of this tau tangential stresses. Because of this, we have quasi like this dependence, but it's not physical. It's correct for averaged value, but we can consider here averaged value. And with our MDR model, we can calculate this distribution of tangential stresses. So thank you for your attention.